All right, here we go again. Unit B, Inferential Statistics, Chapter 3, Confidence Intervals. What the heck is a confidence interval? So that goes back to some things I've talked about before, numbers in the news. And often in the news, we see percentages. Sometimes we see averages. Average could be a mean, right? It could be a median. Sometimes one's more appropriate than the other. The bottom line, though, is whenever they present these numbers in the news, they are estimates. What does it mean to be an estimate? Well, when you estimate something, right, it's not exact. If it's not exact, that means there's some error. So every estimate must have a margin of error attached to it. So what that means is in the media, when they say blank number of people, blah, blah, blah. So here's one, for example, I saw in the news the other day. The whole state of Ukraine and Russia is weighing heavy on the world. It bothers me every day. I wonder if that president's still alive. All the people fleeing. I don't know if you've heard, like through the border to Mexico, there's thousands of immigrants from the Ukraine trying to come in, and we're trying to decide, do we let them come in? Do we not let them come in? Like, why wouldn't we let them flee their country and come here? And what I heard in the news is that 7 in 10 Americans see Russia as an enemy now, right? Where we didn't necessarily see that before this. So 7 out of 10, 70%, okay? They didn't ask me, and they ask any of you? No, right? So who did they ask? How do they get this number? It's an estimate, right? They didn't talk to everybody. So they were estimating, what's that? Yeah. So that's supposed to be a straight line there, make believe it is. So they estimated 70%, 7 out of 10, 0.7. But there's a margin of error to that estimate. So a margin of error means, well, it could be a little bigger that way, could be a little smaller the other way. So the difference to either side is called the margin, right? Think about the edge of a page, right? The margin of the page. So they're more likely saying, well, it could be like maybe 70, I'm going to go with 73% as a high, so 0.73. Or if I go low that same amount, that would be like 67%, 0.67. So I'm estimating a margin of error here of 3%, 0.03 for their survey. When I take the estimate and the margin of error together, I get a whole range of possible numbers that could be the right percentage. Maybe it's more like 71%. Maybe it's more like 68%. And maybe it is 73%. Maybe it's way higher than they thought. Could it even be outside of this? Like, could my margin of error be a little wrong too? The answer is yeah, everything's an estimate. Maybe it's 75%. Maybe it's only 60%. I don't know. So this range of numbers from the middle to the edge with the margin, that range is called the confidence interval. So that's a confidence interval right there. This range of numbers, starting with 67%, ending with 73%, is a confidence interval. So we really have two ways to describe the confidence interval. We can use the center of the interval, which is the estimate, and the margin of error, which is the spread of the interval, kind of like a standard deviation. Or we could talk about the confidence interval by just stating what's the lower end of the confidence interval and what's the upper end of the confidence interval. When you read these articles in the news, though, they just give you the center estimate. They just give you, hey, this is the number we think it is. And then you have to go dig to figure out, well, what's the margin of error? And usually you have to dig quite a ways to find it. And sometimes it's hard to find. And you would maybe have to call the newspaper and say, hey, what was your source on this? Okay, often they list their source. And ask for their source on something? I have, yes. Yeah. These days I email them. And usually I get a response from email. Sometimes I don't. So that's a good question, right? So what if the margin of error is really big? That means the estimate's useless. right? If they said, hey, we think it's 70% with a margin of error of like 40%, like what? 40% margin of error. So you think it's somewhere between what, 30% and 100%? That's a useless estimate. Yeah. So if the margin of error is too big, it's a pointless exercise. Shouldn't even speak that number aloud, whatever they think that number is. So usually we're looking for a reasonably small margin of error, which means we need a reasonably high sample. Okay. Now, so what I'm going to do is I'm going to go find that article that said 7 out of 10 Americans see Russia as the enemy now, and find their information. And I'm picking a source that I know I can always find their information. If I went to the straight news article, I would have to dig, like a lot of times I'll read something in the East Oregonian or the New York Times or the Wall Street Journal, and I'll have to dig to try and find the source of it. Because they won't have it directly, they'll reference it. So then I got to figure out where's the reference from. Oh, it's some university. Then I got to go to the university and dig through their stuff and try and find it. And sometimes I usually have to write to somebody. Can you share the paper with me that had this information in it? Because I really want to know more. So let's do it. All right, so I am going to share with you a Google Sheets where I have a link to the article about Russia. Let's put Russia first here. And remember, when you do share stuff with Google, sometimes it is restricted at first. And even if you copy the link, nobody can see it. So mine is restricted. So I got to make sure I make it so that anyone with the link can view it. Then I can copy the link and get it to everybody. Okay, so I'm going to get this to you guys in a couple different ways. Those of you in Zoom, I'm going to put this in the chat. Those of you looking at this in YouTube in the future, check the description of the video. Where'd my chat go? There it is. And those of you in the classroom, I'm going to pop this into Canvas right now. All right, so here's my spreadsheet. We're also going to jump into Stat Key in a minute. Okay, so those of you in the classroom, if you could go to the announcements, I'm going to post a new announcement. 7 in 10 Americans view Russia, oops, if I could spell Russia, as an enemy. Oop. And here's the sheet hidden behind some cute text. And if you reload the announcements right now on the course homepage, you should get that sheet link there. All right, so everyone get into my sheet if you want to. I see people jumping in there right now. If you're having trouble getting to it, let me know. I'll find another way to get it to you. All right, so here's the original article I found from the Pew Research Center. And they're one of many sites I go to that do research that newspapers use to post stuff. And sometimes the newspaper will go to them, hey, can you help us do this research? And then the newspaper will publish it. So then down below, they say that's 7 out of 10 Americans. And then there's a whole bunch more detail about it if you wanted to read more about that. Now, what I want to know here is, okay, they're saying it's 70%, but what's their margin of error? How many people did they sample? I need to know that to figure out their confidence interval. All right, so usually it's down at the bottom. But on the upper right here, I see a report materials section. So I'm going to look there. So I'm going to try the complete report and see what that says. So what I'm trying to figure out now is, what is their margin of error? How many people did they sample? All right. And sometimes these are really hard to read. Sometimes they're not. Here we go. For this analysis, we surveyed 3,581 people. So I got a sample size. All right, that's part of what I need to know. So I'm going to add that to my chart here. So let's move, oops. Come on, move, there we go. Let's see, what do we use? What letter do we usually use for the sample size? N, right? Yeah, so I'm going to write the word sample size here too. And call it N. And N was 3,581. I get that right? 3,581 people. All right, so that's one thing to know. They claim that the proportion of Americans, so whenever they state something like that in the news, the proportion of Americans who view Russia as an enemy right now is 70%. Is that a parameter or a statistic at this point? It is a parameter. Yeah, they're attempting to measure the whole population, and they say, we believe the population parameter is 70%. Okay. So they believe it. Do they know it? No. All right. Now, and they're going to measure their belief. Remember, probability is a measure of one's belief that something will occur. And so they have a measurement of that belief here too, we'll look at. So I need to know that too. So how sure are they of that? So there's that 70% figure again. That's the parameter. Somewhere here, they're going to talk about, maybe I'm in the wrong draw. It's probably at the end. We want their methodology. Oh, there we go, methodology, okay. In the methodology, they'll talk about their, okay, so here we go. The margin of sampling error, margin of error, for the full sample of 3,581 respondents is plus or minus 2.3 percentage points. So now we get their margin of error, okay? So I was guessing it was around 3%, they say it's 2.3%. Okay, there are ways of calculating margin of error. We're going to slowly work on that over the next 4 weeks. All right, one more thing I need to know is I need to know how sure are they in that estimate? And they're going to give me a percent about that. The most common one is related to our 95% rule. It's here somewhere, waiting. Here we go. They're using a 95% confidence level for this survey. So I want to explain what that 95% confidence level means. And if you watched the video I posted Monday, you already saw something like this for a different set of numbers. Okay, so things I need to know. I need to know the sample size. I need to know the sample statistic, which is their estimate of the population parameter. So at the moment, those are one and the same. That's the 70%. I'm going to call it the sample statistic here. And their sample statistic for a population proportion is P with a hat on the top, which is hard to get in a spreadsheet. So I just call it P-hat. And I put the at in the dash in there because otherwise it looks like a misspelling of fat, which is kind of weird. All right, and there's, usually we state it as a decimal, so I'm going to state it as 0.7. Let's see, what else did I need to put in here? Their margin of error. I'm just going to call it the margin. Sometimes we abbreviate the margin as the ME for margin of error. Another way to state it is the, let's see, error bound on the proportion, EBP. I will write that down in just a second what that means. I'm going to put that in there too. That's my margin of error. And they were saying that was 2.3%, which would be 0.023 as a decimal. All right, now based on those two numbers, I can calculate the lower and the upper value. So I'll do that in a second. But before that, I'm going to put the confidence level in here. And their confidence level, often we abbreviate that as CL for confidence level. You'll see that written on my notes sometimes. And they said it was 95%. I'm just going to type 95% for that. Let's make this a little wider. And then based on that information there, I'm just going to do a quick calculation of the lower and upper ends of the confidence interval. Upper. So here I'm defining my confidence interval. I can. Thank you for asking. Sorry, I forgot to zoom in. I'm having a slow Wednesday. Okay, is that better? All right. Yeah. All right. So the confidence interval, the lower number is going to be the 70% minus that. So I'm just going to go equals and click on the 70% minus the 2.3%. And then they want it to fill down. It's probably not a good idea. Equals 70% plus the 2.3%. Right, which is kind of what I was drawing the picture of before on a number line, but I was guessing at 3%. So now I have these numbers. And usually when we're doing the calculations, we do it in decimal form. And then when we're writing sentences to people, we put it in percent form. Okay, so I'm going to start it there. Questions on what I got so far? So I started with the 70%, right? And then I said, all right, what's your margin of error here? How close do you think you are to the actual real population proportion, and they say we think we're within 2.3 percentage points of the actual number. So that means their estimate is it could be as low as 67.7% and as high as 72.3% of the number of the proportion of Americans who view Russia as an enemy right now. All right, now if we read more details about their study, we'd see they didn't call kids, they only called adults in this study. And so we might refine that a little bit, right? That this is the proportion of adults in America who view Russia as an enemy, not all people in the US, for example. Now, the 95%, what does that mean? So that I'm gonna draw a picture of. Let's go back to the notes. Now, that goes back to the 95% rule from statistics, descriptive to statistics, 95% rule. And the 95% rule said that we expect most data to be within 2 standard deviations of the mean. Now, I'm generalizing the idea of mean a little bit here because this isn't an average that I have, this is a proportion. So in this case, the proportion is my mean. It's the middle of what I'm targeting. Now, next thing is, what does data mean in this context? And what data means are other similar samples. So data, what is data here? Data would be other similar samples. What does other similar sample means? Well, they would all have to have the same sample size, which was 3,581. And they would have to be random and representative, which is what Pew hoped to have, a random representative of US adults. So if I make tons and tons of samples, so I go out and hire 1,000 people and I say each of you needs to contact a nice representative random group of 3,508 people and ask them, do you think Russia is an enemy of the US now? And they're going to answer yes or no or something else. And you're going to count the yeses. And then you're going to say, okay, this many said yes out of the total, and you're going to report back your proportion. Is it going to be exactly 70%? No, your sample might be a little more, somebody else's sample might be a little less. There's going to be sample variability. Every sample is going to be different. If we make a graph of all of those different samples, then what we're likely to see is a relatively bell-shaped histogram. And we're predicting that right in the middle of that histogram, the centermost number is going to be 70%, 0.7. And the Pew one claimed that 2.3% below, so that would be 0.677, and 2.3% above, which would be 0.723. Those were the lower and upper estimates of where they think the real one lived. And what this 95% rule tells us that if we did do 1,000 other samples, just like this one, that 95% of those samples would be in this region right here. 95% of other samples of other, there we go, samples would be in this region right here. This kind of graph, when we're graphing proportions from other samples, right? So what is this a histogram of? This is a histogram of proportions from many other similar samples. Whenever I have a histogram of statistics, it's called a sampling distribution. Section 1 of chapter 3 was all about what the heck is a sampling distribution. We need sampling distributions to build these confidence intervals. And there's several ways to go about doing it. This quarter, we'll learn about 2 ways to construct a confidence interval. And again, there are many other ways to do it. A histogram of proportions. Proportions of what? Well, in this case, it's the proportion of people who say Russia is an enemy of the United States. Similar samples, what does that mean? Well, a different group of 3,581 US adults, right? We just do a whole bunch of those. Now, StatKey can run a computerized simulation of us doing a whole bunch of other samples. So we're gonna jump over to StatKey and make that happen next. So let's take a look at that. Now, to do this in StatKey, I actually need the number of people that said yes to that question. I don't have that number yet. Can I find it? Well, sure. I know that 70% of that 3,581 said yes. So I can just calculate that number. So let's go back to the spreadsheet, get that number and go to StatKey. So I'm going to squeeze a line in between the sample size and the statistic here, insert a row above there. And this I'm going to call X. And all X is the count of people who said yes. So the count of the yeses. Well, I don't actually have the count, so I have to multiply the 70% by the 3,581. So what happens if I take this times that? And sometimes it's not going to be a whole number. Okay, well, why not? Well, when they did the calculation of the yeses over the total, do you think they got exactly 70%? They got pretty close to 70%, and they just rounded it to 70, right? They used some rounding rule to come up with that. So what do you think? It's probably more like 2,507 people said yes, probably. So I'm going to squeeze that number over here. It was probably 2,507 people that said yes. If I recheck the proportion here, what happens if I take this number divided by that one number? Let's do it over to the side. This divided by that. I get pretty darn close to 70%, right? But am I going to report in the media? The proportion we think of Americans that think Russia's an enemy is 0.700837755, right? I'm not going to say that, right? I'm going to say 70%. Okay, so sometimes when you reverse calculate the number, the count, you're going to get a decimal and then you're going to round it. No big whoop. All right, so we're almost ready to go to StatKey. Just a couple other notes here. Whenever we calculate a sample proportion, it's called P with a hat on the top. And it is our best estimate of the population proportion. The population proportion is just called P. So my claim that is P hat is approximately, wavy equal sign, equal to P. The sample statistic is approximately equal to the population proportion. Okay, that's always our assumption. Otherwise, we have nothing to say. Other important fact is that P hat is always the favorable answers, X, divided by the sample size, N. Which I could view instead as a multiplication equation. So alternatively, I could write it as X is equal to P hat times N, which I had to do here, right? Because Pew told me the proportion and they told me the sample size, but they didn't tell me how many people said yes. I had to reverse calculate that. So X is just the favorable outcomes, the number of people that said yes here. So this is the count of favorable outcomes. Count of favorable outcomes. In this case, favorable outcomes are people that said Russia is an enemy of the US. Who said yes to that? That's a favorable outcome. Count them up. No, they were saying, how do people feel about what's going on with Russia? And there's all kinds of things like that. Are you concerned about Ukraine being attacked? Do you think Russia could be a problem for us? Does that make them an enemy for us, right? And people said yes, no, or maybe they were given some other thing to say, right? Like, remember the question I asked a while ago, or the study we looked at about whether students feel procrastination affected their grades, right? So in that case, if we're concerned that procrastination does, then a favorable response was that I said, yes, procrastination is negatively affecting my grades, right? So favorable response, it could be a positive thing, it could be a negative thing. It's just whatever we're trying to measure, whatever we're trying to count. Yeah. So favorable just means whatever we're interested in at the moment. And this time it happens to be, do people feel Russia is an enemy of the US? I know being an enemy is not a favorable thing. We'd rather have friends, but that's what we're asking about right now. All right, stat key time. Let's play with stat key. So find your way over to stat key. You should do just a search for that. So I'm just going to go search for stat key. My computer will probably remember it. Maybe not. It's not being friendly to me today. Lock 5 statistics. That's what I want. Does anybody know why it's called Lock 5? Anybody read the cover of their book? There's 5 authors to our book, and all of their last names are Locke. It's a weird coincidence, huh? It's not. Yeah, it turns out this mother and father professor couple gave birth to 4 kids, and 3 of them are statisticians also. Just kind of. Yeah, I believe there's another sibling that isn't a statistician, is my recollection. I met one of them at a conference, and she was talking about her weird family of mathematicians, and then the outlier. Yeah, the mother and father teach at universities, and 2 of the kids teach at a university, and the other kid is the lead statistician for the Miami Dolphins, which sounds like a fun job. Okay, so what are we doing now? So in the first couple of weeks, we were playing with the descriptive statistics column. We are now playing with confidence intervals. And when I use a computer simulation for confidence intervals, they are referred to as bootstrap confidence intervals. Don't ask me where the word bootstrap came from, but that's what they're called. So are we doing a mean, median, standard deviation, or proportion here? We're doing a proportion, right? So I got to click the right button. So I'm going to click on the CI single proportion. And then since my data probably isn't already in there, right, I have to go to edit data. And they want the count and the sample size. Do we have those? The answer is yeah. We came up with a count of 2,507. So 2,507. And then we came up with a sample size from Pew of 3,581. Make sure I got that right. Okay, yeah. And then I just click OK. Now, so the computer then looks at those numbers, and it says on the right, the original sample had a count of 2,507 with a sample size of 3,581, and that gives you a sample proportion of 0.700, right? Now, what the computer then does is it basically makes 3,581 slips of paper, and on those slips of paper, it writes 2,507 yeses, and the rest are no's, and it puts them in a computerized hat. And then what it does is it shuffles that hat up, and then it sticks its hand into the hat and pulls out a piece of paper and sees whether it's a yes or a no. And it puts the paper back in and does it again. And it puts the paper back in and it does it again. How many times is it going to do it? 3,581 times. And it's going to get a new sample. Is that sample going to be exactly the same? The answer is no, because they put the yes or no back in each time. So I'm going to click the generate one sample button. And so the computer, again, shuffled up all my yeses and nos. And this time when it drew from the hat, it found for me 2,543 yeses, which gives me 71%. My guess is each of you got a slightly different count in your new bootstrap sample, right? Because it's a randomization. Now, it put a dot down here for that new one. So I can do that again, hit generate one sample. And what you should see is those dots end up in different spots on the bottom. And if you point to one of those dots, the bootstrap sample will change, the second box down on the right will change to whatever dot you're pointing at. And you can see sometimes you get higher than 70% of people saying yes, sometimes you get lower. Like my low right now is 68.6%. Did anybody get lower than that? 67.5. Okay, did anyone get higher than my 71%? 73%. Wow, Andrew's on a roll with the high and the low there. You did a lot. Okay, now notice there's a bunch more buttons than generate 1 or 2. We can generate 10 new samples. Okay, now or I could generate 100 new samples, or I could generate 1,000 new samples. What the hell just happened there? All right, every dot represents a group of 3,581 people. And all we recorded was what percent said yes. How many different samples do I have here? At the moment, I have 1,114 different samples here. How big are each of those samples? 3,581 people each. Okay, I'm creating what's called a sampling distribution. In this case, it's a distribution of sample proportions. To get a reasonable response from the computer simulation, I need at least 6,000 of these. So start generating thousands of samples till you have over 6,000. And I have an old laptop at home that starts to drag when I do this. So if your computer's a little older, you might be waiting a few seconds for it to generate. And it depends on the browser you're using. Because actually, when you went to the site, you downloaded the code that does all these computer simulations. You're not running somebody else's computer right now. This is running live on your computer. So slower computers, this runs slower. Okay, so next thing. We want to calculate a margin of error based on this. To do that, we have to decide how confident do we want to be in our answer? Well, the standard is to be 95% confident. Okay, so to do that, there's a two-tail button in the upper left of the graph. Click the two-tail button. And the computer says, how about we put 95% in the middle? So what it did is it counted up how many dots I had. It knows there were 7,114. It said, I want 95% of those, but I want the 95% in the middle. So it found the lower 2.5%, made a mark. Then it scooted up to the end and it said, okay, show me where the upper 2.5% of these samples are, draw a line. I just want the ones in the middle. And it's telling me, if you look at the bottom there, I see the number, I didn't mean to click that. I see the number 0.685. So it's saying that's the lower end of this confidence interval. And the upper end for mine is 0.715. And my guess is you have very similar numbers, if not the same numbers. Yeah. So if it's a big enough sample size for a proportion, the simulations are going to come out almost exactly the same, even though at first all our numbers were wicked different. And that's why I said you got to run thousands of these for it to start to even out. Okay. We just made a confidence interval. Is it different than the confidence interval from Pew? And the answer is probably, because they used a different method than we're using. So they're going to have a slightly different margin of error. All right, questions on what I have so far? Next thing I want you to do is I want you to make a rough sketch of this on a piece of paper. All right, so I'm going to try to do this with you here. So you have your version in front of you, or maybe you're watching a video or watching me and doing mine. So I'm just going to move mine out of the way for a minute so I can redraw it. Whenever I redraw these, I just draw a smoother version of what I see there. And wouldn't you agree that when we talked about different kinds of distributions way back in like week 1, oops, my page is slowing down there. That is a relatively bell-shaped symmetric histogram, isn't it? Yeah, so I'm just going to smooth that out on my paper. All right, so new page. Just going to draw what I see there, and my computer is not happy today. Yours went completely down over this? Oh my gosh, I'm so sorry. It's not supposed to do that. All right, so I'm just going to draw a little line here for the x-axis, and then draw my best bell-shaped symmetric curve there. And I always put a line down the middle, and at the bottom of that line, I'm going to put that 0.7 that I started with. And then I'm just going to put a mark there and a mark there. I'm going to put that 95% in the middle here. And then I got 0.685 on the left, and I got 0.715 on the right. So what I have right here is I have a confidence interval. So my confidence interval, I'm going to call it a CI. Often we write it in parentheses. So parentheses state the left number, 0.685, comma, state the right number, 0.715. So if somebody says, hey, just what, as simply as possible, tell me your confidence interval. That's it right there in parentheses. And there'll be homework problems where you have to state a confidence interval like that in parentheses. What it means, we'll get to in a second. Let's see, what's the margin of error? In StatKey, the best way to come up with the margin of error, because again, this is a randomization, right? This is flipping coins over and over again to see what might happen based on a given sample. The graph is not perfectly symmetric, which means the endpoints, my 0.685 and my 0.715, they're not necessarily going to be equidistant from the center, but they'll be close. So to even that out, instead of like finding the distance from the center to the right or the center to the left, what I'm going to do is I'm going to find the whole distance across and cut it in half. In StatKey, that's the best way to calculate your margin of error. So for me, the ME, the margin of error, is going to be the 0.715 minus the 0.685. How far are they apart? And then cut that in half. That's the best way to do it. All right, let's see. I guess I need a calculator for that because I'm a little slow today. So I'm just going to make a note down here according to StatKey. And remember, a spreadsheet is a calculator, but you could whip out a handheld one. For StatKey, the lower for me was 0.685. Oops, 685. And the upper was 0.715. And then to make that calculation for the StatKey margin of error, I have to use parentheses to do the subtraction first. So equals parentheses, take the big number minus the lower number, and then slash divide by 2. I get 0.015. Anybody else get that? A couple nods, cool. All right, so again, I like to use a spreadsheet as a calculator. You can use any calculator you like. So my margin of error is 0.015 or 1.5%. I could also state it as. So that's the best way to get the margin of error. So I'm just going to make a little note of that up here, slightly different color. My ME, we got 1.5% versus their 2.3%. Yeah. Why are they different? Well, again, I mentioned that we're using a different technique for finding the margin of error. Okay, I'll talk about their technique in a few weeks. It's a little more complicated. All right, so what did we just find right here? Well, what we're doing is we're estimating the population parameter, right? The population parameter is still 70%. Okay, will there be a little bit of deviation in the StatKey graph from the original sample? The answer is yes. What? Oh, come on, you can do it. StatKey is really slowing down my Chrome browser today. Come on. All right. The 0.7 that it's putting in the bottom of my graph in the bottom middle here, sometimes, yeah, there we go. Sometimes it'll be a little bit than the original sample statistic of 0.7, because again, what it's doing is it's looking at all 7,114 samples that I made. It's adding up all those proportions and dividing by 7,114. And sometimes that might be a little bit off from what the original sample was. So again, my point is sometimes when we run these simulations, the sample proportion that I started with up here is not going to be exactly the same number I see in the middle of my distribution down there. We always stick with what the original sample said for the center of our estimate. Okay, we're always going to go with that, even if the number down here in StatKey is a little bit different. But for the interval, to get the endpoints of the interval, we're always going to go with the two numbers it gives us here. Okay, so I just want to restate what this confidence interval means in a couple of different ways, and I want to restate what the 95% means and what it doesn't mean. And then we'll try another problem. All right, so based on our simulation, here's what we now know. We are 95% confident that the proportion of people in the US who view Russia as an enemy I don't think I need to capitalize enemy, do I? Enemy is, there's two ways I can finish this sentence, okay? So option one is to say between the two numbers we calculated for the interval. So I would say between with two E's, what was it, 68.5% was our low, and 71.5. Right. Yeah. So yeah. And so I'm not writing the media statement, the press release. I'm writing the semi-technical explanation of what we just calculated there, right? But in the media, right, we wouldn't state it that way. We would just say the 70%. And if somebody wanted to look up the fine print, then they could get more details. So option two is to state our estimate of the number, the middle, the point estimate, and the margin of error. And there's a few ways to do that. So I might state it like this: is within 1.5% of 70% would be another way to state that, right? So I state the spread and the center. Option one, how about we call this one option two? There we go. And again, every language is versatile in the way you state the things. There's lots of other ways I could state that. I could just say it is 70%, and then I could say with a margin of error of 1.5%, right? Or it's about 70% with a margin of error of 1.5%. But when I ask you to tell me what your confidence interval means, I want one of these two versions of here. And again, an option 2B might be is 70%, and then I could just say with a margin of error of 1.5%. And there'll be plenty of times where I'm going to say, hey, calculate a confidence interval based on this data right here, and then tell me what the confidence interval means, and you're going to throw a statement at me like this right here. What does the 95% mean? So I explained that in a kind of technical way. Basically, it's based on the idea that we reproduce this sample thousands and thousands of times. Now, are we really going to do that in reality? The answer is no. It costs probably a ton of money just to get those first 3,581 people to answer the question. We're not going to go and do that same thing thousands and thousands of times. That's not feasible. So it's a confidence in the process. So what it means is 95% of similar samples will contain, nope, we're not ready for contain, will have an interval that contains the actual proportion. So if at this moment in time, we could get an answer from every adult in the US, we would know the exact percentage, but we can't do that. There is, in this moment in time, an exact percentage. People are going to say yes, or they're going to say something no, and we count the yeses out of how many adults are in the US, right? That number exists, we just can't get it. Now, it's a fixed number. So I can't say that there's a 95% chance that my interval caught it, because it's not moving around to be caught, right? Either I have an interval that it's in, or it's just not in that interval. Right. So all it is it's assurance in our process, that this process repeated over and over again. If you did 1,000 of these samples, 950 of them would actually have the real proportion in it, and then 500 of them would just miss it, or 50 of them would miss it, excuse me. They wouldn't have it in there, and we won't know which one's which because we'll never have the original number. Okay. So the book goes over a bunch of examples of what it doesn't mean and what it does mean. It's a weird idea. My more important thing is not that one right there, but you definitely need to know that. It's, can you tell me, can you throw the 95% and the confidence interval in a sentence in context? That's the bigger point I want you to be able to do here. I know, explaining this is the hardest part, right? We push a button on the computer, we get these numbers, oh crap, what do they mean, right? That's the hard part. Yeah, Emma? Yes. Yeah, so they generally use a theoretical approach to calculating these that involve a whole bunch of formulas, and we'll get to those formulas like in week 9. No, they just do one sample, and it's based on that. The only feasible way to do it besides the bootstrap method that we're doing here is the theoretical method, which involves these crazy mathematical formulas that have been studied, for hundreds of years. The computerized version we're doing now is a newer technique because computers are so fast these days, right? 50 years ago, we couldn't do this. The computer wasn't powerful enough to do this simulation that many times. It would have taken, when I was in high school, my dad had a computer and it cost like, I don't know, $20,000, and it was way slower than my iPhone, and it didn't have all those colors, right? My iPhone, which is an iPhone 5, right? I'm still on an old phone, is 100 times more powerful than the computer that we paid $10,000 for back in the late 80s. And that computer was not capable of running these simulations unless I gave it a week and didn't touch it the whole time. Right. So our computers these days are super fast. They allow us to do things we couldn't do before, and these simulations are one thing there. Okay, and again, the simulations are randomness, and the simulation is only good if the sample is good. If this is a biased, non-representative sample, then I just created a bunch of crap. But if I believe that this is a good random representative, meaning it does depict the population as a whole, young, old, male, female, other genders, whatever, ethnicities, then this method is effective for accurately generating a range of possible answers called a confidence interval. And somebody had to write the program to do that. And the question is, did they do a good job writing this random simulator program? I hope that they did. I believe that they did. Our computer programming abilities these days are astounding, the things we can pull off. So I have pretty good faith in the programmers that made this happen. Yeah, so at this point in the world, there's 2 main techniques for calculating confidence intervals. One is a theoretical approach based on some crazy formulas we'll talk about in week 9, and the other is a computer simulation tool like this, StackKey. All right, let's try another problem. And actually, let's stand up and stretch.